We're doing the derivative of the natural log function today, which is maybe a little illegal, but we're going to do it anyways because I think it's got enough value. So the natural log is actually just the inverse of the exponential function to the base e. The logs are basically exponential functions with the x and y exchanged, and if you look at the graph, it's the reflection in the line y equals x. We re-express this so that we have an expression in terms of y, and we write this as y equals the natural log of x. So this expression and this expression are equivalent. The only difference here is that we have this one expressly in terms of y versus having the y implicitly defined up there in the inverse function that we obtained just by exchanging x and y. Okay, now there's a tricky patch when we get finding the derivative here. Y is a function of x. And so when we take the derivative of y with respect to x, we wind up with y primed. Okay, so maybe that wasn't too tricky, but you're going to see we need to apply the chain rule when we get taking the derivative of this inverse function. Okay, so this is going to give us the pattern for the general derivative, x equals e to the exponent y, because I can't do this natural log one. I just don't know what it is yet. I'm going to take the derivative of both sides. So the derivative with respect to x of this side, and I'm going to take the derivative with respect to x of this side, e to the exponent y. And here's the sneaky patch. This I have to apply the chain rule to because y is a function of x, and so this is a function of a function. I need to apply the chain rule, but it's going to be easy. Just watch. Okay, the derivative of x with respect to x is 1. Just use the power rule. That's easy. Okay, the derivative of an exponential function is the exponential function, so this is just e to the y. But y is a function of x, and so I have to multiply the derivative of the outside by the derivative of the inside, which is just y primed. Now, what's fantastic about that is that, oh, that looks like a y to the 1. Okay, there, that's a y primed now. Anyways, what's great about this is I now have y primed somewhere in my expression, so I'm going to isolate that, and that's going to tell me exactly how to take the derivative of this natural log function. And so y primed is equal to 1 over e to the exponent y. But wait a minute, e to the exponent y is just x. It's just x. So y primed is really just 1 over x. How could that be easier? Well, I can think of some ways that might be easier, but y primed is just 1 over x. And if you go over here and you look at this logarithmic function that we made sort of by reflecting it in the y equals x line, and you just sort of think about what the derivative might look like, it all starts to make sense because here you can see that the derivative is positive and it's a really large number. Okay, and then as we continue along the curve, the derivative actually gets smaller and smaller. And so, yeah, this really does look like that reciprocal function. The trick here, though, is that x always has to be greater than 0. Okay, I cannot take the log of a negative number. So we have to stay cognizant of the restrictions on our domain when we're looking at these at doing the derivatives of these log functions. Okay, let's do this business of taking the derivative of a logarithmic function. We're going to do a few that require the chain rule. We're going to look at alternatives to that using properties of logs, and then we'll do one question. So this is not going to take that long, and I think it's worthwhile knowing how this works. Okay. Y is equal to the natural log of x squared. All right. So this is one of those chain rule questions. So let's do this one. Let's do this one with the hup 1, 2, 3 here. So there's u, it's equal to x squared. Du dx is equal to 2x. Okay. And y is equal to the natural log of our inside function, which we've called u. So ln u sounds like a threat. All right. And so the derivative of the outside function with respect to the inside is 1 over u. There we go. And dy dx is equal to dy du times du dx, which is just equal to dy du is 1 over u. And then du dx is just 2x. And 1 over u is, remembering that u is 1 squared, is 1 over x squared times 2x. So this just winds up being 2 over x. Now I have to think about my restrictions here. I can't take the log of a negative expression, but this is x squared, so it just doesn't matter. That's always going to be positive. So I can't take the log of 0. Okay, so log x can't be 0, doesn't matter anyway. When I get to this expression, x can't be part of the original function. So also the derivative doesn't exist there, so obviously. Okay, let us do y equals the natural log of x to the 4th. Let's see what happens this time. I am not going to use the super elaborate chain rule system. I am just going to hot dog this. I'm going to use what I call the chain rule song. Derivative of the outside, which is just 1 over x to the 4th, times the derivative of the inside. There we go. 4x cubed. Okay. Oh, once again, the only restriction here is x can't be 0 because this is always positive. And look at that. The x cubes cancel there. This is just 4 over x. Oh my goodness. The natural log, the derivative of the natural log of x squared was 2 over x. The derivative of the natural log of x to the 4th is 4 over x. We seem to have a pattern, and we kind of do, okay? So if y was equal to the natural log of x to the 7th, say, for example, in this case, the only difference is that x has to be greater than 0 because this is an odd power. I can't take the natural log of a negative number, so x has to be greater than 0. So y primed is equal to 7 over x. It's just that simple. Is it some sort of witchcraft? The answer is no. We can actually look at this just a little bit differently. Using the power rule for logs, we can reorganize this, and you're going to see why that pattern emerges when we use the chain rule. Okay, y is equal to the natural log of x to the exponent 7. My log rules for a power, I can rewrite this as 7 times the natural log of x. Now all of a sudden, now I can, when I take my derivative, I just use my constant rule. So constant, the derivative of a constant times a function is the constant times the derivative of the function, and the derivative of the natural log of x is just 1 over x. So there we go. Boy, we could have not done a bunch of chain rule stuff if we just thought about that a little bit sooner. All right, let's look at one more example, and then we'll be on our way. So, I better say y is equal to the natural log. Whoa, look how complicated this is, of x squared minus 4. Okay, so we've got a function of a function again. We're going to need to use our chain rule. We're just relaxed, though. We can use our chain rule. And the derivative of log is easy, so we don't have to worry too much about that. But we do have to think about this restricted domain, because, look, this is like a parabola that's translated down 4 units. So graphically, it looks like this. And if we're really sharp about it, we know that that's at x equals -2, and that's at x equals +2. This parabola is below the x-axis when x is between -2 and +2. So now we have to just put on the restriction of the domain here. Another way of looking at it algebraically is x squared minus 4 has to be greater than 0. So that means that x squared has to be greater than 4. So that means that positive x has to be greater than 4, and that means that negative x has to be, not 4. Negative x has to be greater than 2 as well, which means when I shift my negative sign over, x has to be less than -2. So this function exists when x is less than -2 or when x is greater than +2, okay? Otherwise, when you look at that function, it just disappears in between there. Okay. Let's not do the u dy du dx thing. Let's just do the derivative of the outside. I'm not even singing the song. Just 1 over whatever that is, times the derivative of the inside function. Derivative of that is just 2x, okay? So this is actually just 2x over x squared minus 4. I see my derivative does not exist when x is equal to 2 or -2 because that makes the bottom 0, but it doesn't matter because x never is 2 anyways. The original function is not defined there. So there's my derivative. So that's the derivative of the natural log function. You just put 1 over whatever is inside the natural log function and do the derivative of the inside. So you're just using the chain rule. It's pretty easy. Just remember you've got restrictions on your domains. And tomorrow, we actually need to understand this just so that we can do the derivative of other exponential functions.